Hello everybody. We're going to do our lecture in just a minute on matter, and it's kind of an introduction to chemistry, but like I said, I like to show you some of the demonstrations that normally you would see if you were in class with me. So what I have here today is some potassium iodide, and the other thing here is lead nitrate, and you can see if you hold it up to the camera that these are basically totally clear liquids. You can't see anything in them. They look like water. Of course, you wouldn't want to drink them. They're highly dangerous. But anyway, what I want to demonstrate for you today is just to show you how the properties of a compound change once you see a reaction. So we have two things here, right? But once they react together, we're going to see something totally different. So it's only really kind of tangentially connected to minerals, but it's still kind of cool. So I'm just going to mix these together, and you can take a look at what happens. So you can see that this is, I hope it shows it really well on the camera, but this is like a vivid yellow now. So anyway, what I formed is actually lead iodide. That's the yellow cloudy stuff that you see in here. So anyway, wow, it's so yellow. If you were here, you would see how vivid and vibrant it is. But anyway, hope you enjoyed that. I'm going to click you over to the lecture now. Hello, everybody, and welcome now to your lecture number 5. This is going to be on matter. Matter is the building block of minerals. Minerals are the building block of rocks, and rocks are the building blocks of the earth. So that's why we start with matter. And we're going to go into minerals next, and after that, rocks, right? So that all makes sense. So anyway, hope you got your lecture assignment number 5. I got mine right here in these beautiful spiral-bound lecture assignment packets. I only had one person pick them up so far, so hopefully some other people come, instead of bothering to print it out on your own. Besides, you get a chance to visit me and also visit OSO campus. But anyway, here's number 5, lecture assignment number 5 on matter. And I'm going to start going through these things here. Let's see. Boom. Why isn't it working? Here we go. All right. So like I said, minerals are the building blocks of rocks. And what are minerals made of? They're made of atoms. And that's what we're studying right now, right? Atoms and chemistry and matter right now. So there's some beautiful different examples of... whoops, I'm trying to get my... see here, I have this electronic stylus. And I'm writing on the lecture assignment like that's going to work. So I got to go to my little pad right here. So anyway, sorry. So we have quartz, mica, calcite, pyrite. That's fool's gold. That's what we're going to be talking about. Next lecture, we talk about minerals. But anyway, what makes up the minerals? They're made up out of atoms, right? Now, minerals are very special because minerals have a lot of special properties or very unusual properties. And I'll introduce some of those in the next lecture. But the reason that they have a lot of those properties is because they have a very specific sort of atomic arrangement. Now, if you take a look at these, I guess for you, they kind of look like they're over here, right? Right there. So anyway, if you take a look at these atoms, notice that in the minerals, they're very precisely arranged, right? They're not just thrown in there willy-nilly. They're very precisely arranged, and that's actually what gives minerals some of their very unusual properties. And I think that's why a lot of people think minerals are magical or something like that. They do have a lot of weird properties, and I don't know if that counts as magical, but I think that's part of the reason why. They have very, very unusual properties that arise from this very specific atomic ordering. More about that in the next lecture. So we're going to kind of jump out of order here. Lecture assignment number 5 here. If you take a look at number 11, it says, what are the 5 most common elements in the crust? Well, I actually answer that right here. So that's kind of the first thing I answer. So, we have the periodic table of elements. We have 92 naturally occurring elements, but only a handful of them are really common in Earth's crust or in Earth itself. So 99% of the rocks that compose Earth and the metal that composes Earth, it's made out of just a handful of different elements. So you can see them here. We talked about this in the last lecture, but oxygen, silicon, aluminum, iron, magnesium, calcium, sodium, and potassium, right? So remember that potassium, the elemental symbol for potassium is a K, which is a little bit unusual. Sodium is a Na, right, which is a little bit unusual, right? So it comes from Latin terms or Greek terms. Nickel, where's all that nickel? It's all in the core. So we don't have very much nickel here in the crust. We have a little bit, of course, but all that nickel is in the core. The bulk of it's in the core. And sulfur, too, which a lot of that sulfur is in the core as well. Okay, so let's go back to atoms and talking about atoms and atomic structure. So, question number one, I say, what's the three fundamental subatomic particles? List their charges and masses in terms of AMU. So we have three subatomic particles, right? Proton, neutron, electron. Protons have a positive charge. Neutrons have a negative charge, neutral charge. Electrons have a negative charge, okay? Protons and neutrons are in the center, like the nucleus. Okay, we call it the nucleus of the atom, and the electrons orbit around it. Now, when I say that electrons orbit, don't think of like planets orbiting the sun. They don't orbit in that way. That they do occupy orbits or shells that are at a certain distance, a certain average distance away from the nucleus. Okay. So that's the sense in which we mean that they are orbiting. But don't think that these atoms go, in this slow progression around the nucleus. That's not what happens. If anything, they're sort of vibrating within a certain fixed distance away from the nucleus. That's what we mean by an electron shell. Okay. Anyway, the charge of the electron is -1, charge of a proton's +1, charge of a neutron's neutral 0. Okay. Now let's talk about mass. The mass of a proton is 1 AMU. What's an AMU? It's an atomic mass unit. It's defined as the mass of basically a proton. So it makes sense that a proton weighs 1 AMU. But it's just defined that way because to try to use kilograms or something like that, metric system units for something like this, it's so weird because, how much does a proton weigh? Well, it weighs about 10 to the negative. Oh, actually, there should be a negative right here. 10 to the negative 24 grams. So that's a trillionth of a gram. So it's not really very helpful. So to make things easy on ourselves, scientists do like to actually make things easy. I know it seems difficult at times, but to make it easy on ourselves, we just call the mass of a proton 1 AMU. We came up with our own unit. So it's fine to just put that there. Now, an electron, a proton and a neutron weigh about 1 AMU. An electron actually weighs significantly less. Weighs 0.0005 AMU. So it's 5/10,000ths of an AMU. So electrons weigh very little compared to a proton or a neutron. So the vast majority of the mass of that atom is centered in the nucleus. The vast majority of it. Okay. Okay, so I talked a little bit about shells and electron shells. This is very important because the reason that minerals form, they form from, atomic bonding, different atoms bonding with each other. And the reason that bonding happens is because electron transfers. And the reason that electrons transfer from one atom to another, or they're shared among atoms, all has to do with the outermost electron shell. And I'm going to explain what that means because it probably doesn't make any sense right now. So like I said, electrons are split into these different shells. Okay, so you can see this picture right here of carbon. Notice that in the first shell there are 2 electrons. In the the second shell there are 4 electrons. Okay. Now the first shell can take a maximum of 2 electrons. Don't ask me why, because you could ask me why, but it has to do with quantum mechanics and quantum theory, and it's a big open, it's a big can of worms, is what I'm trying to say. So it's not something you need to know for this class, so don't worry about it, but suffice to say that the first shell takes 2 electrons. The second shell can take 8 electrons, okay? Now, here's a question for you. This picture you see of carbon, right? Why are there only 4? I only see 4, right? 1, 2, 3, 4 electrons in that second shell. Thought you said it could hold 8. Well, there's only 4 because carbon only has 4. Notice that carbon is element number 6. That element number, what's called the atomic number, is equal to the number of protons, right? Atomic number is equal to the number of protons. In the case of a neutral atom, that means an atom that is neutral, electrically neutral, has no net charge, the number of protons is equal to the number of the electrons, right? If you have 6 positives, you have to have 6 negatives in order to be neutral, to balance everything out. So, has 6 electrons. There's 2 in the first shell, there's 4 in the subsequent shell. So that's why there's only 4 instead of 8 there. Okay. Now, here's a little thing about atoms. Atoms are most stable when their outermost electron shell is full. Let me say that one more time because it's important. You got to know this one. Atoms are most stable, happiest, let's say, they're happiest when their outermost electron shell is full. So here's a question for you. How many electrons can fit into the second shell, the outermost shell of carbon? 8, right? So if it can take 8 and it only has 4, is it full? No. Is it happy? Not happy. What does it need to be happy? Well, it can do 2 things. It can either somehow lose these 4 electrons. That's kind of hard to do. It's kind of hard to rip electrons away from the nucleus. Or it can somehow gain 4 more electrons, either by sharing or by just electron transfer. We'll talk more about that later. So let's go look at some more examples of how electrons are split up among the various shells. Let's look at oxygen. Very common element, right? It's one of the most common elements in the crust. It's actually the most common element of the crust. Crust is kind of strange to think about it this way, but the crust is not, I can't say mostly made of oxygen, but almost mostly made of oxygen. It's almost a majority oxygen. Isn't that weird to think of? The crust is mostly oxygen, but it is. It's very close to being true. So it's almost 50%. So anyway, here's oxygen. And has how many atoms? Or sorry, how many protons? 8, because it's element number 8. It's atomic number. Okay, that means if it's neutral, it's going to have 8 electrons. The 2 are in the first shell. That's going to leave 6 in the subsequent second shell, the outermost shell. Now, are those electrons happy? Well, not exactly, because it wants to be full, right? The atom wants to be full. So it is going to it can take 2 different tacks here. It can try to shed those 6 electrons in the outermost shell. That's really hard, right? Think of magnets. Here, I'm going to disappear for a second and go get some magnets. Hi, I'm back. So I brought magnets. But anyway, I was just trying to say that, is it easy for an atom to shed its electrons? Is it easy for it to lose electrons? Well, not exactly, because just like magnets, or maybe static electricity, there's a force attaching the electron, which is negative, to the positive protons, right? So these are the neodymium rare earth element magnets. They're real strong. It's hard to pull these things apart, right? They like to be connected together. So it's just like magnets, right? It's hard to pull those things off. It's a little bit easier for it to just attract 2 more electrons and be full that way. Does that make sense? Okay. So anyway, let's go on to chlorine. Chlorine is element number 17. That means, hey, hello. There it goes. Element number 17. That means it has 17 electrons in the case of a neutral atom. So 2 in the first, 8 in the second. That brings us to 10. 7 in the last one. Okay, now this third shell, just like the second shell, can take a total of 8 electrons. So it only has 7 out of 8, right? 7 out of 8 here. 1, 2, 3, 4, 5, 6, 7. Not happy. What is it going to do? Is it going to shed those 7 extra electrons? No. Think of the magnets again, right? It's too hard to pull those electrons off, although it can be done. it's easier for it to just attract one more electron. And that's usually what chlorine does. Okay. Last case, and this is another interesting one I want you to take a look at. Argon. Argon is element number 18. It has 2 in the first shell, 8 in the second shell, and 8 in the third shell. So third shell full, the outermost shell full. Yeah, 8 out of 8. It is happy. Doesn't want to bond, and it doesn't bond. Argon's atoms are noble gas elements, and they just kind of float around, and they are fine, and they don't bond, and they don't care about anybody else but themselves, and that's it. Okay, they don't involve themselves with anybody else because they don't need anybody else. The other atoms, they only get bonded together because they need the other atom to be happy, right? To be full, to be stable, to have that full electronic valence state. Okay. Valence, by the way, that term valence, let me write that up there. Valence refers to this outermost shell. Think of a veil. You know how you put a veil over something, right? It's like the veil of the atom. Okay, it's going over and covering the atom. It's the outermost valence electrons. So that's what that word means. So anyway, there's our periodic table of elements. I want to say something about this periodic table here, right? We have all these different elements, and they're all arranged, you'll see, in a table. And that's not just arbitrary. It's not like someone just thought, hey, it'd be cute putting the atoms in a table. It actually means something. So I'm going to explain the meaning behind this periodic table now. These columns are very specific. They're arranged this way because the columns, which are called families or groups, are just like real families, right, that you're in. You know that in your family, there's some similarity between you and your brothers and sisters and your cousins and aunts and uncles, etc., right? So it's the same thing with atoms and elements. The atoms and elements of a family, there's some similarity to them. So this first group that's over here to the far right, it's actually called group number 18. It consists of the noble gas elements. And just like argon, which we already studied, they're all kind of similar. They're all just stable, and they're full outermost shells, and they're unreactive. They don't react with anything else because they don't need to. The next one, close to it, the next family, which is family number 17, it's like chlorine. We looked at chlorine, right? It is a halogen. These are called halogens. These all have one electron missing from their valence state, from their valence shell. Okay, so they need one more electron to be happy. This makes them highly reactive because they are desperate to get that one last electron. So fluorine, very highly reactive. Fluorine is so reactive that it'll actually eat away glass. If you put some piece of glass in fluorine gas, by the way, fluorine is a gas. It's a purple gas. It's really weird looking. It will actually eat away the glass. Pretty amazing. Chlorine, very highly reactive as well. Very poisonous and deadly as well, right? Why are they so deadly? It's because they're highly reactive, and they're highly reactive because they're desperate for that one last electron in its outermost valence state. Next to it is group number 16. These are the elements like oxygen, sulfur, selenium. These are all needing 2 electrons. Okay, they need 2 electrons to be happy, so they're pretty reactive as well. Now, things get kind of complicated. I don't want to talk about atoms too much over here. In this group, these are called the transition metals here. But you'll notice that there's really only one element that is common in Earth that's among the transition metals, and that's iron. Everything else is like how much vanadium or chromium is in the Earth. It's not really too much. Things also get kind of complicated over here, and you'll notice that we do have silicon here, and aluminum, which are pretty important. but I don't talk about them too much because their chemistry gets a little bit more complicated. Sodium and potassium, however, are easier to understand. Magnesium and calcium are easier to understand. So we'll talk about those a little bit later. So let's look at sodium. We're going to look at this group number 1. This is hydrogen, lithium, sodium, and potassium. All of these, so all of these actually have, let's look at lithium. Lithium's pretty easy to understand. So you have a nucleus, right? It's element number 3, so it's going to have 3 electrons. So there's 2 in the first shell. There's 1 in the second shell. Now here's an example of something. Yeah, it is hard to rip an electron away from the nucleus, but it's also pretty hard to attract 7 electrons too. So with lithium, sodium, potassium, hydrogen, hydrogen's a little bit different, but let's say lithium, sodium, and potassium, they are going to be very inclined to just give away. That's going to go away and lose that extra electron. And then it'll just have the 2 in the outermost shell and it'll be happy. Okay. Beryllium in this column number 2, group number 2, beryllium, magnesium, calcium. Magnesium and calcium, both pretty common on Earth. Beryllium is actually one of the rarest elements on Earth. Not very common. But magnesium and calcium are. So magnesium and calcium want to give away. They have a similar problem. They have 2 electrons in the outermost shell. They want to get rid of it, and so they're inclined to give those 2 electrons away. So these guys, sodium, potassium, they're generous. They want to give away an electron. These atoms, magnesium and calcium, they're very generous too. They want to give away 2 electrons. Okay. So think about this. They're going to want to combine with oxygen, chlorine, fluorine, things like that. They're going to bond with those because that side, these guys want electrons. These guys over here want to give away electrons. Okay? So that's how that all works. Iron is common, like I said. Silicon's common. Aluminum's common. These guys mostly want to give away. Okay, this wants to give away 4. This wants to give away 3. Iron usually wants to give away 3 or 2. It gets complicated because there's this thing called crystal field splitting. It gets complicated with iron, but I just want to give you an idea why it wants to get rid of 2 or 3. Okay, because most of these elements, they only want to give away a certain number. Okay, so anyway, let's take a look at how chemical bonding happens. All right, so you have sodium is going to lose an electron. Okay, sodium's going to lose an electron, so it's going to go from neutral sodium to sodium plus an electron. Okay, when you take an electron away from sodium, it makes sodium have a net charge. Get ready here for number 7, number 8, number 9, and number 10. I'm going to answer these right now. Okay. What is an ion? An ion is an atom with a net charge. An ion is an atom with a net charge. So when sodium loses that electron, it takes on a net charge, right? Because now it doesn't have enough electrons to balance out the positives in its nucleus from the protons. Does that make sense? Chlorine is going to take that extra electron, and guess what? When it takes an extra electron, it makes it negative, right? So it becomes an ion as well because it has a net charge. And then sodium plus and chlorine negative are going to combine together. Okay, so here's another kind of cute way of thinking about it, how sodium and chlorine met and bonded together. So sodium atom is unhappy because it has 1 too many electrons. He'd like to have a perfectly full shell, right? Chlorine, she's also unhappy because she needs to have 1 more electron to be perfectly full. So what's going to happen? Well, sodium is going to give up that electron. It's going to ionize. Now this sodium is sodium plus 1. It's going to ionize, and it's going to become something called a cation. Cation is an ion that has a positive charge. Hint, hint, number 8. Okay. Chlorine is going to accept that extra electron. It's going to take on a negative charge, right? It's going to become chlorine negative. Now that is called an anion. Spelled right there, hint, hint, number 9. Okay. Now they're bonded together, right? Sodium gives chlorine its electron, and now they're bonded together. If sodium moves away from chlorine, it's going to take its electron with it, and chlorine will lose it, and then both will be unhappy again. And they don't want that. They want to be stable. And, it's kind of funny. Chlorine is highly dangerous as a gas by itself. Sodium is highly dangerous as a metal by itself. Explosive. If you swallowed pure sodium, you'd go kaboom. You'd blow up. So both will kill you. But when they're bonded together, they're safe because they're not reactive anymore. They've already reacted with each other. They're happy now. So instead of reacting with your body tissues, they've reacted with each other. And now it's salt. It's NaCl. It's sodium chloride. It's salt. And you need it to live. Isn't that weird? By itself, sodium and chlorine, they'll kill you. But then when they bond together, you need it. You need it to live. You can't live without it. So that's how it all works. Some examples of cations, right? Calcium plus 2, potassium plus 1. Remember that calcium is in this group, right? And it has 2 extra electrons. So when it gets rid of those, it ionizes, it takes on a plus 2 charge. Atoms in this group take on a plus 1 charge because they have 1 extra electron in its outermost electron shells. Sulfur takes on a 2 minus. Chlorine takes on a minus 1. Okay. So here, this is the answer to number 11 and number 12. Number 11 we answered right in the beginning, right? I said, what are the most common elements of the crust? Well, I laid them all out. Here they are, right? Silicon, oxygen, aluminum, sodium, potassium, magnesium, calcium, etc., etc. Now I'm asking, when these things ionize, right? I hope that you understand by now, when things ionize, when these atoms ionize, they don't just become any number. It's not like a plus 4, plus 8, plus 7. It always goes to a certain number, okay? When iron ionizes, it's either plus 2 or plus 3. When carbon ionizes, it's either plus 4, silicon plus 4, okay? Does that make sense? They're both plus 4. Look how they're both in the same family. When sodium ionizes, it's always plus 1. When potassium ionizes, it's always plus 1. Does that make sense? Yeah, because they're in the same family. When magnesium ionizes, it's plus 2. When calcium ionizes, it's plus 2. Does that make sense? Yeah, because it's in the same family. Okay. Look at the oxides and the sulfides. They're both negative 2. Does that make sense? Yeah, because they're in the same family. Okay. Fluoride and chloride, when they ionize, they're both negative 1. Does that make sense? Yeah, because they're in the same family. Okay. So it all makes sense. The periodic table all makes sense. It's not just like somebody came in and thought, oh, this will be cute if I put lithium here, and this will be cute if I put aluminum here. No, it's not like that. It's all logical. Okay. So that's how it works. All right. Now, we get to something that is a little bit hard. So pay attention now. So I don't know if you're doing whatever, distracting yourself from this lecture. Pay attention now because this part's kind of hard. Okay, you looking? You paying attention? Okay. So let's go on to number 13. And go ahead and read the question. And it says, I'll read it for you. Take a look at the following possible mineral formulas. Which do you think could be the formula for a real mineral? Assume the bonds are ionic and the formula must be electrically neutral. Okay. So we're talking about matter and atoms and bonding so we can understand minerals. minerals, when they bond and they make a chemical compound like this, they have to be electrically neutral. What does that mean? I'll show you. Take this mineral, this beautiful green mineral, which is, by the way, one of the most common minerals in the earth, the lower mantle. It's called periclase. It's just magnesium oxide. Okay, take a look at magnesium oxide. What is the charge on magnesium? It's a +2, right? What's the charge on oxygen? -2, right? Makes sense? We already talked about this in the last slide. What is +2 plus -2? 0, right? Let's look at another example. Silicon dioxide, which is called quartz. Quartz is one of the most common elements in the crust. Silicon, the charge on silicon was what? We said +4, right? There it is, +4. Oxygen is -2, but there are two of them. So -2 plus -2 equals -4. -4, silicon is +4. When you add them together, you get 0. You get it? Does it make sense? Let's look at another example. This is a harder example. Magnesium 2, silicon O4, oxygen 4. That is the mineral olivine. Beautiful mineral, peridot gemstone, very common in the upper mantle. Okay. Magnesium has a 2 charge, and there's 2 of them. Okay, 2 times 2 is 4, so that's a +4. Plus 1 silicon, right? That's another +4. Plus 4 oxides, -2 each. That's a total of -8. 4 plus 4 plus -8 equals 0. So what you have to do now is take a look at number 13, A, B, and C, and do the same thing. Add up all the charges of all the atoms that are in the mineral formula there and see if it ends up being electrically neutral. If it's electrically neutral, then that could be a valid mineral formula. But if it's not electrically neutral, that's indicating that that maybe isn't a real mineral. Okay, so that's how you figure that out. All right, so all of that kind of bonding that involves ionization and transfers of electrons from one atom to the other, that's called ionic bonding. So everything that we had looked at previously was called ionic bonding. It involves ionization and complete transfer of one electron or multiple electrons from one atom to another atom. Okay, so that's called ionic bonding. Now we're going to look at another type of bonding, which is also somewhat common within the mineral world, and that's called covalent bonding. Covalent, remember that valence refers to that outermost electron shell that is so important in chemistry and in bonding and minerals. Okay, so important. Remember, you want to have a full outermost valence shell. Okay, covalent means sharing the valence electrons. So in covalent bonds, instead of having charged ions, we're going to have atoms that share electrons. So all of those rules we just learned here about electrically neutral mineral formulas, that only applies when we're talking about ionic bonding. When we're talking about covalent bonding, those electrically neutral rules don't necessarily apply. Okay. For example, here's a mineral where it doesn't apply. A mineral where it doesn't apply is diamond. Diamond, the mineral formula of diamond is C, carbon. Carbon is +4, right? So obviously it doesn't apply there because you'd have a net charge of +4. That doesn't make sense. But diamond isn't bonded together with ionic bonds. It's bonded together with covalent bonds. So the bonds of the electrons of the different carbon atoms are shared. So let me show you what I mean. Oxygen, let's look at the compound CO2, carbon dioxide. Okay, oxygen shares its valence electrons with carbon. Remember that carbon wants 4 more valence electrons. Oxygen, on the other hand, wants 2 more. But you know what? If everyone shares, they can actually achieve a full electron shell. So let's count how many electrons are in oxygen now. 1, 2, 3, 4, 5, 6, 7, 8. Happy. Carbon. 1, 2, 3, 4, 5, 6, 7, 8. Happy. 1, 2, 3, 4, 5, 6, 7, 8. Happy. Everyone's happy. Okay. So how did they get all happy? They all shared their electrons together and shared the number that they all need in order to be happy. Okay, and have a full outermost valence shell. Notice that carbon, all of carbon's electrons are shared, but only half of oxygen. Each oxygen is only sharing half of its valence electrons. Okay, half are shared, half are what are called lone pairs. Okay. H2O, another example of covalent bonding. Okay. So covalent bonding is common, like I said, in graphite, which has a mineral formula of just carbon, and diamond. One thing that's really, I think a lot of students find this very cool, is that diamond has a mineral formula of C, graphite has a mineral formula of C, and they're so different. Graphite, by the way, is the stuff that's in your pencil lead. Isn't that cool? So it's pure carbon. Diamond is pure carbon. What's the difference then? They're made of the same exact thing. What's the difference? The difference is how those atoms are arranged. That's how the atoms are arranged. The carbon atoms are arranged in the diamond. That's how the carbon atoms are arranged in graphite. So that's what makes the difference. And it's pretty crazy when you think about how big a difference atomic bonding makes. Okay? Diamond is totally different than graphite, as you well know. So we talked about number 13, talked about number 14, and I just talked about number 15. Diamond and graphite have the same exact mineral formula, right? They're both made of pure carbon. What do we call that? We actually call that a polymorph. I'll spell it for you. Polymorph. Poly means many, morph means shape. Many shapes. Refers to the many shapes of the atomic arrangements. So here's another question, number 16. Can a mineral be composed of only one element? Yes. And you can see more examples right here, right? Graphite, only composed of one element, carbon. Diamond, only composed of one element, carbon. There are other things too. Gold, that's a mineral. Copper, that's a mineral. Iron, that's a mineral. How about silver? That's a mineral, but only consists of one element. Okay? So that's how that all works. Okay. I want to talk now about a very special kind of molecule. And that molecule is called the silicate molecule. Silicate molecules are very, very important because they are the building blocks of Earth. Most of Earth is composed of silicate molecules. It's a very, very, very special molecule. So again, if you're zoning out or not paying attention, please pay attention now because it's very important. All right, remember that Earth's crust is made up, 75% is just made up of 2 elements, silicon and oxygen. Okay? Silicon and oxygen love to bond. They love bonding. And when they bond, you have silicon. It's going to bond. Actually, it's going to create a molecule with 4 oxygens surrounding it. Okay? Silicon plus 4 in the center, right there. And it's going to create something that kind of looks like a pyramid. It's not actually a pyramid. It's called a tetrahedron. A pyramid actually has 5 different faces. A tetrahedron only has 4, but it kind of looks like a pyramid. So silicon 4 plus, and then we have 4 oxygens around it, right? These 4. So 4 times -2 for the oxygens, right? -2 charge on each oxygen, that equals -8. 1 silicon, right, times plus 4 equals plus 4. If we add these together, you see that we get a net charge of negative 4. So the silicate molecule is what we call a polyatomic anion. It is a negatively charged anion, but it's not just one element. It's composed of 5 different atoms, right? 4 oxygens with 1 silicon. Okay, and it forms a tetrahedron. Now, these are going to bond with different cations to achieve electrical neutrality. Okay, so for example, SiO4, the silicate molecule, silicate tetrahedron, has a negative 4 net charge. And it can bond with 2 irons, for example. And each of those irons has a plus 2 charge. That brings it to a plus 4, right? So plus 4 and negative 4, it achieves electrical neutrality. Okay, so that's a real mineral. It's called phthalate. It's a type of iron-rich olivine. Okay, so it's 2 cations of iron bonded with 1 silicate tetrahedron. Does that make sense? I know that's kind of complicated, but it's very important because these silicate tetrahedra are the building blocks of Earth. Okay. Most of the rocks you see around you are based on this silicate molecule. Okay. So, most common class of rock-forming minerals, number 17, the most common class are the silicates. So many of the most important minerals are the silicate minerals. Okay. Now we need to talk about another thing about silicates. It gets a little bit more complicated. So again, pay attention because this is going to get kind of more complex here. We have 6 kind of different common types of silicate molecules, all right? And they're all here. These are the 6 most common silicate minerals. And they are in a very certain order. Do y'all see this? Pay attention here. They're in a very certain order. It goes from quartz to feldspar to mica to amphibole to pyroxene and finally olivine. They are in an order of what's called silicate interconnectedness. Okay? And I'm going to go through and show you exactly what I mean. In the meantime, make sure that you fill out number 18 here with these 4 in this order. Okay? Quartz is the most interconnected. Olivine is the least interconnected. Silicates are, and we're talking about silicates, how the silicate molecules are interconnected. I know you might be thinking, why does that matter at all, how the silicate models are well, you're going to see that it makes a big, big difference for the behavior of that mineral. Okay. So number 19, you can do this now. Draw out the silicate tetrahedron. Okay, so draw that picture that you see right here to the right there. Okay, and you can get all that. Sorry, this has got so much writing on it now. Okay, and then you can use this to get the charges on everything and make sure that the net charge on the silicate tetrahedron, -4. Okay, that's the net. Does that all make sense? I hope it all makes sense. Please tell me if it doesn't make sense. Okay, ask me. You can call me during my office hours. All right, so we got number 19 done. Let's talk about some more of the silicate interconnectedness. Okay, so these are the 5. You're going to need to okay, you're going to get so sick of this stuff because I present this today and the next lecture and the next lecture because it's hard and you need to hear it a lot of times and you need to know it. So there are these 5 silicate structures. It's how the silicate molecules are interconnected. The first one is called the isolated structure, the isolated tetrahedra. It is typified by minerals such as olivine and garnet. Olivine, you can notice that in olivine, the tetrahedra don't touch. The tetrahedra don't touch. Okay, you all see that, right? The next type is pyroxene, right? Pyroxene, you'll notice that they're called single chains. single chains. Every tetrahedra is connected by at one point to the next to its neighbor, right? So you see that's connected there, and it forms like a chain. Okay, so they're sharing with maybe two other. Every tetrahedra is sharing with two others. Okay, sharing with two others. Now look at the double chain. The double chain, it's two single chains connected together. Those are the minerals called amphibole. One of the most common amphibole minerals is hornblende. Look at that nice little mineral formula. Kind of a nasty one. If you ever take mineralogy and you become a geology major, you have to memorize all these things. But anyway, amphibole. So do I make you? I don't see. No. Okay. So amphibole. Notice how every tetrahedron is sharing not with two now, but with three. Okay, you see that? 3. So that tetrahedron is sharing with 3. Okay. Now let's look at the two-dimensional sheets. These are the micas. Okay, the micas actually are really cool. If you take our lab, you'll see that mica actually splits into sheets. Okay. So you notice that every mica, 3 oxygens are shared. Right, so actually it's like a combination of different the double chains that see. So I can actually say some of the tetrahedrons here are sharing with 3. Some of them are only sharing with 2. So this one is sharing with 3. That one's sharing with 2. That one's sharing with 3. That one's sharing with 2. Right? See, so that's a 2. That's a 3. That's a 2. That's a 3. That's a 2. That's a 3, etc. But look here. All of these are 3, 3, 3, 3. And of course, this is supposed to go on, for infinity in every direction. So you have to kind of visualize that. All right. So more interconnectedness as we go through the micas. Finally, we get to the last one. That's the framework silicates. In the framework silicates, you can only understand it. You can't see it two-dimensional. You can only understand it. It's three-dimensional structure. This is the quartz and the feldspars. These are all interconnected, and all 4 oxygens are shared. All 4 oxygens are shared. Okay. Important rules. Silicate tetrahedron. I'm trying to draw these. I'm sorry for the spikies. I hate these spikies. Silicate tetrahedron. You can draw them with triangles like you have to do in number 20. Silicate tetrahedron only. Here are the rules, guys. Guys and gals, pay attention. Silicate tetrahedra can only attach to each other and connect on corners, on the points. So they only do that, right? Not sides. So you never see this ever. There's one tetrahedron. There's another tetrahedron. You see how this tetrahedron is sharing 2 oxygens with this one? No. Never happens. It only shares, it can share all of its oxygens, but it has to share with 4 different individuals. Okay? It can only share on points, not on sides, and not on faces. Okay? Faces can't be shared. That, if they do that, it brings the silicon atoms too close to each other, and they don't like that. Okay? So that's it. You have to draw, for number 20, you have to draw the isolated structure, the single chain structure, and the double chain structure. Okay, so you just copy those pictures. That's all you do. Right, these ones right there. Okay, we figured out everything, right? So hopefully you're good now. There's some key points: bonding, ionic bonding, and covalent bonding. Ionic bondings by electrostatic attraction, covalent bondings by electron sharing, anions. Right? Anions are negatively charged particles. Cations are positively charged particles. Chemistry of a mineral, it's always a cation plus an anion in the case of ionic bonds. Okay. Bonds can also be covalent, involve sharing of electrons between bonded pairs. Silicate molecules are the building blocks of rocks and minerals. They are organized by the degree of silicate interconnectedness. And that's all she wrote. So, that's a long lecture. Thought it was going to be shorter. Well, sometimes it ends up that way. Hope you enjoyed it, though, and I will talk to you next time. and enjoy the show. Bye-bye.